From the quiet hum of your computer to the birds chirping outside, our world is just filled with sound. It's everywhere, all the time, shaping pretty much every moment of our lives. But have you ever really stopped to think about what sound is, like on a basic, fundamental level? Well, we're about to dive in and find out.
Right? We hear them, we make them, we can even feel a really loud sound rumble in our chest. But what are they? In this explainer, we're going to pull back the curtain and uncover the hidden physics behind every single sound you've ever heard.
All right, first things first, let's start at the very beginning. We're going to follow the journey of sound, from its start as a simple type of energy, all the way to how it becomes that complex thing we call hearing.
So at its absolute core, sound is just a form of energy. It's not a physical thing, it's not matter, it's pure energy, just like light or heat. And you know the rule about energy, it can't be created or destroyed. Think about it, when you clap your hands, you're literally converting the mechanical energy of that motion directly into sound energy. Boom!
Okay, so if sound is energy, where does it come from? Well, it turns out the source of every single noise, from the quietest whisper to a massive thunderclap, is the exact same simple physical action.
What's the trigger? What sends this energy out into the world? The answer is so simple, it's kind of beautiful. Something, somewhere, is moving.
This classic experiment is so cool because it makes the invisible visible. When you hit a tuning fork, you hear that clear note, right? But you can't see anything moving. But if you touch that same vibrating fork to a tennis ball just hanging there, the ball gets kicked away. That right there reveals the secret. That invisible motion, the vibration, that's creating the sound.
And that's all a vibration really is, a super fast back and forth wiggle. Every single sound you have ever heard started with some object vibrating, pushing and pulling on the air, or the water, or whatever is around it.
And seriously, this is happening everywhere, all the time. When I'm speaking right now, my vocal cords are vibrating. When you hear a guitar, it's that plucked string vibrating. That buzzing sound from a bee, that's its wings vibrating like crazy. It is the universal source of all sound. Okay, so we've got a vibrating object. Got it. But how does that wiggle travel from, say, a ringing bell all the way across the room to your ear? It's not magic, it's this really fascinating chain reaction. Here's a crucial rule. Sound can't travel through nothing. It always needs a medium, a solid, a liquid, or a gas to carry that vibration along. It's why in the total vacuum of space, you could scream at the top of your lungs and there would be absolute silence. There are no particles to carry the sound wave.
Okay, so picture that vibrating tuning fork again. As it moves forward, it pushes the air particles right in front of it together. It literally squishes them, creating this little pocket of high-pressure air, and we call that a compression.
Then, just as quickly, the fork moves backward. When it does that, it leaves a little bit of empty space behind it, so the air particles spread back out to fill that gap, creating a pocket of low pressure. That's a rarefaction. A sound wave is just a continuous chain of these compressions and rarefactions traveling through the air. This type of wave makes sound what we call a longitudinal wave. The best way to picture this is with a slinky. If you push the end of it, you see that compression travel down its whole length, right? The coils move back and forth in the same direction the wave is moving. That's totally different from a ripple in a pond. There, the water moves up and down while the wave moves forward. That's a transverse wave. Now, this is a super important point. The air particle that got pushed by the bell doesn't fly across the room and into your ear. No way. It just bumps into its neighbor, which then bumps into its neighbor, and so on, like a line of dominoes. It's the energy that travels, but the particles themselves pretty much stay put, just wiggling back and forth. So we've got this invisible wave of energy zipping through the air. But how do our brains take that one wave and interpret it as all the thousands of different sounds we hear? Well, it's all about decoding the language of the wave itself.
It really just comes down to two key things. First, you have pitch, how high or low a sound is. That's all about frequency, which is just how fast the wave is vibrating. A really fast vibration gives you a high-frequency wave and a high-pitched sound, like a violin. Then there's loudness. That's determined by the wave's amplitude, which is basically how much energy it's carrying. A big, forceful shout creates a high-amplitude wave, while a soft whisper creates a tiny, low-amplitude one.
The medium sound travels through also changes its speed dramatically. Just look at this. Sound travels more than 17 times faster through solid steel than it does through air, Why? Well, in a solid, the particles are packed in really tight, so they can pass that vibration along way more efficiently. This is exactly why you can sometimes feel the rumble of an approaching train through the rails long before you can actually hear it through the air.
So now that we get the basic physics, we can get into the really cool stuff. Some of sound's amazing abilities. We've actually learned to harness these properties to create incredible technologies that let us use sound to echo, to see inside things, and even to heal.
I'm sure we've all experienced this. An echo is really simple. It's just a sound wave that hits a big, hard surface, like a cliff or the side of a building, and bounces right back to you. It's just like a ball bouncing off a wall.
And here's a wild fact that's all about our own biology. Our brain needs about 1/10 of a second to tell the difference between two separate sounds. Because of that, to hear a truly distinct echo, the wall or cliff has to be far enough away for the sound to travel there and back again in at least that amount of time. And in the air, that journey requires a minimum distance of about 17.2 meters. Pretty specific, right?
And we use this idea of reflection all the time. A megaphone is shaped specifically to bounce the sound waves forward into a focused beam. A stethoscope uses a bunch of reflections inside its tubes to guide the very faint sounds of a heartbeat right to a doctor's ears. Even the curved ceilings in big concert halls are designed to perfectly reflect sound so everyone in the room can hear clearly.
But what about sounds we can't even hear? So the human ear can typically pick up frequencies up to about 20,000 vibrations per second, or 20,000 hertz. Anything with a frequency higher than that is called ultrasound. It's totally silent to us, but it can be incredibly powerful.
We use these high-frequency, invisible waves for some amazing things. They can vibrate dirt clean off tiny, delicate machine parts. Engineers use them to find hidden cracks deep inside metal beams. And of course, in medicine, ultrasonography uses reflected ultrasonic waves to create those amazing images of our internal organs, or even to shatter kidney stones without ever making a cut.
So in the end, sound is so much more than just noise. It's this entire invisible world of vibrating energy, traveling in waves, bouncing off everything, and carrying information all around us. It really makes you wonder, what other invisible forces are out there, shaping your reality in this very moment?